Okay, so I hope that after this interesting news and the pizza, everybody is awake, not sleeping. I try to do my best to not to let you fall asleep. So, my name is Attila Tamas Zimler. I used to work as I work as a developer, but not at the moment as employed one. But I try to design piece of software. So, who am I? I was introduced to programming in really early age. I was 10, and kind as a hobby by my father. So we tried to design software for playing. I don't know if you know these kind of games, like you have to turn to page 93 to do some actions. You know that. So we tried to implement those kind of things in C64 with BASIC, and from there I gradually learned more and more programming languages. So it kind of kept me just playing with, and then I went to a technology school, so I got the informatics part for it as well, and then I started to work as a programmer, and then I applied for the university. So why is this interesting? It's interesting because during my university studies, they tried to introduce software development from a different kind of concepts. So everything was derived back to set operations, and like they defined this kind of thing. So if you have a set and an e that is an I that is an infinite an element of an infinite set of a finite set, then for each of the I in that set, ai is not 0, then you can have a state space which basically describes the variable state of the program. So that was the first concept that they introduced. So each of the sets represent in practical a variable, and you can have these elements for it. So like you can have one for an integer, another one for a boolean, and that's kind of combined gives you the all of the variable and gives you this state space. So from there, we went to that a program is basically a series of these set transformations, and this is the A star star part of that equation. Sorry for the quality, I had a little bit of technical issues with that. And this series is selected based on the starting values, the starting state values. So it's kind of describes that based on the input, we are going to perform some operations that transforms this the state of the program, and then we are going to have as a last state the result of the program. Do you think it's look familiar? Yes, it's kind of like a tuples in F sharp, and like functions in F sharp as well. So this is interesting because the method itself that was used during the university courses was to actually design programs from just being able to describe the problem as a function that you need to transform something to something else, and it was basically mathematically proved, so you could design a correctly functioning program. And on third semester lecture, the theory was also extended, so you could do parallel programming with it. Basically the same stuff. You define your problem, you have some theses that are proven to be correct, and you need to apply them to your problem, and you could get a fully functioning parallel program that is not going to crash you can prove that mathematically it is correct, it's going to deliver what you expect, of course, if you don't make any miscalculation in the equation as well. So, but that part is up to you, but the tools are already given, so it was really interesting. And this theory in the basics also give you how to describe an object as a functional thing. So you could use that for modeling objects in F#, the theory itself. So what is a class or a type in F#? It is composed from 3 parts, which is basically a function that is going to give you an equation, a logical expression that what this type represents. It don't really exist in your program because it is the transformation from your state from your state space to what actually in real life that type means. So like you won't be able to put a red car into your program, but you will be able to model it as that the color is red, the wheel count is 4, and things like that. So you could have that, and this function is basically theoretically transforms it to a red car, which is doing something. The other thing is that could be represented in your program, but not necessarily represented, is an invariant function, which means which should be true or should transform to true. It means that your actual object is in correct state. So this invariant function should give you true when you enter to any of the methods, and should also give you true when you leave those methods. So it means that you leave the object itself in a consistent state. So this could be added to the program to actually validate your components. You don't necessarily have to add it. You have to think about it because you don't want to leave your object in an inconsistent state, but could be used then as an assertion. So so you could tell that this state wasn't expected when you enter into the method or when you leave it. And the third part is a set of programs as defined on the previous slide, which is basically the operations that you could perform on the type itself. So like increment a variable by 1, or turn the car left or right, or those kind of things. So how could we do this in F#? So the class in F# is actually declared by the type keyword, as it was on the previous slide. In lightweight syntax, you need at least one member definition. In non-lightweight syntax, you could actually define an empty class. And as with any other .NET languages, everything is derived from system object. You can't escape that. So this is how you do on, this is comparison on how you do it in C# and how you do that in F#, because most of us actually know C#, so it's quite makes things easier. So with the, as you can see, the first F# is not really the lightweight syntax, because that wouldn't work. So you need at least one member definition to do that. You can define fields as variables in that function itself, because in this case, basically, the type itself is a function with some sub-functions that you could call, and more or less. Yeah. So, but but this field is actually private, so you can't access it from the outside, and that's good because it makes you automatical. It makes automatical to actually do the encapsulation. So you won't be able to access the state of the object itself from outside. You need to manipulate it through the small programs that are the members through the object itself. And by the way, it's a requirement for the type itself as defined by the theory. So there are a lot of other things that a type needs to be fulfilled to actually be a fully working type. So I tried to simplify the math part so you won't fall asleep on that. It's like a 300 pages book. So the let inside the class is private, and everything up until the first member definition in the part is in the class itself is part of the primary constructor. You can think about that as an initialization code for all your variables. So in this part, you need to set your state space into a consistent state, so it will fulfill the invariant function for the first time of the object. So that's kind of constructing it from nothing to a valid state. If you want to do something in this part, you could use the do keyword. So like printing out something that don't give you any return value, so you can't assign it to a variable. Actually, not a variable, to a value. Yeah. So it just because it's functional, so you don't really have variables. So, and let and do bindings must come before the first member or interface definition in the type. After that, you are not allowed to introduce these kind of things into your class. So this is how it looks. So that's the C# version of it, and you can get a pretty much simplified version for the F#. Members typically make up the public interface for a type, so by default they are public. Another interesting thing is that x.get field is basically, you can just rename your this variable. So it's going to be the object itself. So if you write this.get field, your object is going to, inside of your member function, is going to get called this. If you write x, it's going to call x. And so that's the reason why basically that small line on the bottom is equivalent with the one on the example. Constructor parameters. So this is how you initialize your state space. And an interesting thing is that basically you could use the same name for the inner values. It doesn't really confuse the compiler which one is which one, because it doesn't really exist at that moment. And yeah, let's get into the specialization later. Okay, so there are two kind of way you could update an object in programming languages. One of them is functional, which means that you don't change anything in your object. And the other one is the object-oriented way, which means that you basically change your object itself. So in the functional way, you return a new object with the modified state, kind of like supporting the functional programming that you always have access to previous values that was used as an input, and you give back the output as a different value. So how would you do that? So in functional style object update, basically this is how would you do that. You just create a new value and return that from the member function itself. So the set model is going to have a vehicle type, and that is what is going to be assigned to your value outside of the function. And then you can further manipulate it with different calls, and you are doing the same again and again, and you have access to all of your mid-based steps. So the other way is basically how we used to do that. For that, in object-oriented language, for that, F# supports the mutable keyword. With using this on a value, you can later change it with the update operator, which is that left pointing arrow in here in the slides. This might be the actual expected working way for non-F# libraries. So if you would like to implement a library that would be compatible with other .NET languages, you would probably want to do this way, because other ways the programmer that uses the library would not get what he or she is expecting from your code. So that could cause some surprise. We like the string variable. I always run into that I forgot to assign it. And after that I find it out. So previously we used two set functions on the slide to set the model of the object and to get it back. That's kind of like property. We can define properties in F# as well, because it's a .NET language. And the syntax is that we have to define the property itself, and we then define the two functions that are actually, if you want to use just once, you don't have to define the other one. But probably you want to have a get function that's a parameterless, and you need to return something that is basically with an equivalent type of your property. And you have to have a set function if you would like to assign something to it, and the value of that is basically what is going to be assigned, or what you are going to use. So if you are going to have some calculation, then the input for that calculation. When you define a property with simplified syntax, where you just want to use the default get and set, then you have to assign a default value to that property, so it's not just going to be in the air. It's not doing the same as with the C# language is doing for you, that when you create a variable, it is always initialized. It doesn't really depend if you don't want to use that value. It's going to be initialized. You can override to be initialized to something else, but in F# you definitely have to define what you want as an initial value. So it's basically that what we can see after the field that equals 0 is that initial value. And it's the same as you would get by default in C#. For these kind of member definitions, you have to use the val keyword. So that's going to describe to the compiler that this is going to be an automatic property. And then after with, you could define that you want to get or a set accessors to those kind of things. If you don't want to set accessor, you could just leave that out with the comma, and it's going to work fine. Sorry?
You set the value of that field without the constructor.
No. If you would like to use a parameter for it, then you'd actually Since probably at that point you have access to that value, maybe you could use that. So if you have a constructor parameter that is going to be passed to your type, I guess you could use that. So it's kind of in scope, so I would expect to be able to do that. Oh, actually, it's there. So you can do it. So it's just here in the first example, yeah. No worries.
But can you actually set when you have the ET, the parameter in the constructor, is it mutable or non-mutable?
No,
Can you have
that's a good question, but I don't think it's mutable. It's kind of like unmutable. Okay, the second pair of code is showing how we can inherit classes. So basically you use the inherit keyword and you describe that what type are you inheriting from. In F# you can cast the type, but it makes difference between upcasting and downcasting. It comes from the situation that in way of casting you could cause error, or you could be sure that it's going to be fine. So if you upcast, it should work. It definitely should work. The compiler can check that it is type correct. You won't make any mistakes. So you can replace the type with the actual other one. So it's going to be okay. With the downcasting, however, it's kind of like forcing out type from an upper type. So you just say that, look, I don't care, this is that type of value, and please make to behave like that. But in that case, if it's not correct, then you could get an exception. So you probably have to be aware when you downcast that it can actually throw an exception, and as a best practice, you have to prepare yourself for doing something with that. If you are absolutely sure that it's not going to throw an exception, then on the other hand, probably you shouldn't try to force the cast itself, because for some reason you definitely know that it's correct. So you could write in a way that you don't even need the cast itself. So this is how you do the upcasting. So basically just define another value and just do the casting itself. So as I said, it can be verified by the compiler itself, and it's always safe. The downcasting, on the other hand, is what you try to force. And as you can see here, I am trying to make a car into a motorcycle, so that's going to throw an invalid cast exception. And this kind of thing can only be checked during the execution, so that is the reason why the compiler can't go after you and make sure that it's going to be correct. So that's the reason. So if you want to do a downcast and you want to avoid to have an exception, but you want to do it anyway, you can check the type. So in F# we have this colon question mark operator, which is going to give you a logical value on if that type is actually represented by the actual value that you apply on. And if you think that it's kind of like similar than the downcasting operator, I don't think that it's a lucky coincidence. Because if you think about it, during the downcasting you anyway have to check the type. So probably that gives you a shorthand for that. Okay, abstract methods. If you want to define an abstract class, then you have to apply an attribute to it. So because in C# you have the abstract keyword that you could use, but in F# you don't. And basically in math you don't really think something as an abstract, so I think it's kind of like extension on the functional language itself, so it could support the .NET environment. And you can have abstract functions as defined in the last line for the first example. You can have it with any type. So that's basically the function that needs to be defined when you derive the class itself and you want to make it to a concrete type or you want to use it. And you have to use the override keyword to basically override it. So that's how you could provide an implementation for it. Virtual methods. So technically virtual methods are abstract methods with a default implementation, and composing those two elements you could get something that you don't necessarily have to define as a default implementation, and you can override it. The keyword to define it in your base type is the default keyword, and after that you can use basically the same syntax as with the member keyword. So that's the only difference for it. Accessing base method, basically as like C# you use the base keyword to call the method, and you can just use it in the same way. So this is, without any surprise, exactly the same as C#. Okay, additional constructors. So what we saw previously was the primary constructor of the type, and basically that has to be the most specific ones for your type, because you cannot make it. You have to call that constructor from any of the other constructor that you are defining. So you cannot make it more specific, because otherwise you wouldn't be able to really use that value. So that is the reason behind it, and you can't apply any tricks that I'm going to write something after the constructors and things like that, because the compiler don't really allow you to do that. So there are other ways to define much more specific constructors, but those are not really constructors. Those are just ways of constructing a type with a given state and a given state space. So you introduce additional constructors with the new keyword, and after that you enumerate your parameters, and you have to call your actual constructor, and you have to call it basically as a first line. So you can't really do stuff like I'm going to compute it something and going to put it into an inner let variable in your declaration between the constructor and the type and the type start itself, because that's not going to compile as well. For trickier construct, you could use static methods. That's kind of like, look, make an object with this state, and it's going to create an object and going to set different state space on it, and that's how you basically do a much more specific or otherwise required constructor that you can't really define as an additional constructor. Indexers. So you need to be aware that that's the actual syntax of how you define an indexer, and it's pretty much logical because for the get you have one parameter which is the index and you need to return the value, and for the set you have two parameters which is the index and the value that you want to place into that index, and that how is it work. But in C# you actually operate in the item or items. I wasn't able to clarify it properly if it's multiple or singular collection, which is hidden from you by the compiler itself. But this is not the actual situation in F#, so you can rename that member to anything else and it's going to work. However, if you would like to make it compatible with the C# or other .NET languages that's going to call your code, if you don't really want to make hard your programmer clients who is going to call the library life hard, then you should use this item. Otherwise, it's going to be tricky to access it. So this is the way how you actually use. I think these two slides might be swapped. I'm not really sure. This is the way how you define static methods, and as a conventional thing, F# use it's really just a convention, so you could name it anyway, but it's a good practice to start it with the make and then what you would like to make as a meaningful state. So like if you would like to make it a child motorcycle, then you could just use it as a child motorcycle. From this static function, you need to return the object that you are actually created. That's kind of like evident because that's why you call it. Interfaces. That's the syntax on the first line how you define interface. An interface is an abstract class with only abstract methods, and then you have to basically override everything. I think I'm not totally sure if you need to apply the abstract. You don't? No. Okay. I thought that I might be just missing it, but yeah. So and then you could just inherit it. If you implement the interface, you need to use the interface keyword, and after that, in an inner block, you could just define the members that are related to that interface. So this is going to give you a nice separation on which method belongs to which interface, and yeah, basically the member implementation is just as the same as for the class inheritance. So other than that, it's going to be separated for interfaces. It's going to look the same. Oh yeah.
Yes, you need the abstract keyword for each of the members.
Oh, so you need, okay.
So I think it's the typing preference determines that it's an interface by the fact that it's only got abstract members and they use the interface keyword in its using them.
The other difference is that you don't have the constructor, so it doesn't have parentheses next to the
Yes.
type. So that's why.
You need to be aware that if you would like to pass an object that is implementing an interface to a function that is expecting the interface, without further tricks, you need to specifically cast it to that interface type. So it's going to present itself as the interface.
It's because at a higher level, it's doing an explicit implementation of the interface, not an implicit implementation, which is the standard way you do a C# interface is implicit. So it's if you were to in C#, if you were to implement any interface explicitly, it would be the same as if you implemented an interface in F#.
So, oh yeah, and as last thing, Object expression, basically it's creating an anonymous type that you are going to use. It's a nice replacement for just deriving something or overriding something if you don't really want to use it extended. So if you don't want to use it too much in your code, then basically just as a quick shortcut you could just use an object expression. And within that expression, so you introduce that with the curly braces, within that expression you need to create your object, and then you can override the things that you would like to override with the with keyword, and then enumerating the members that you would like to replace. Like for the toString, you can just return a string, and that's all. So thank you for your